Let's do this other example of matrix multiplication. So this time we are multiplying two matrices that are not square matrices, meaning that these two matrices don't have the same number of rows and columns. Okay. So the way we do it is, let's use the trick. So we write the first matrix here, 1A, 0, 2, 1, 1, K, 0. And then instead of writing the matrix to one side, we move it up, as always, yeah? So we write the other matrix here, 0, pi, square root of 2, A, 1, 0. So the result of this matrix multiplication fills in all this gap. And this is a very big gap. So notice it's a grid with 4 rows and 3 columns. Yeah? And this always happens. So the first matrix here is a 4 times 2 matrix because it has 4 rows and 2 columns, while the second matrix here is a 2 by 3 matrix because it has 2 rows and 3 columns. So we know that the result is going to have 4 rows and 3 columns. And the way to remember it is by doing the trick, by doing this trick of moving the matrix and looking at this gap that we see here. So this tells us the size of the matrix. Yeah. So what's the first element? First element is the dot product of the corresponding row and the corresponding column, as always. So it is 1 times 0 plus A times A. It's A squared. Next element is the corresponding row with the corresponding column. Yeah. So it's 1 times pi plus A times 1. So it's going to be pi plus 1. And so on with the other gaps. So let me do that fast. And that finishes this matrix. So that is the resulting matrix. Okay? So normally we would just write it in a different way, of course. This is just the trick, but normally we would write it. Let me copy all this again. That's how we would usually write it. Okay? So one matrix times another matrix equals this other matrix. Right? Now, what does it mean that these matrices were not square? So they had different numbers of rows and columns. So here I have a nice diagram summarizing the situation. So remember, here we are doing that B times A equals C, which means that the transformation C is a transformation in which first we do the transformation A and then we do the transformation B. Remember, we go from right to left when we do the multiplication. The order of the transformations is from right to left. So it means that we first do the transformation A, and the transformation A is a 2 by 3 matrix. This means that this matrix can act on vectors that are 3-dimensional, and it produces a result that is 2-dimensional. So that's what is written here. We start with 3-dimensional vectors, we apply A, and we end up with 2-dimensional vectors. Next, we have this 2-dimensional vector, and we apply matrix B, which is a 4 times 2 matrix, 4 rows and 2 columns. This means that it can act on vectors with 2 dimensions, and it produces a vector with 4 dimensions. That's why from 2 dimensions, we apply matrix B, and we end up with a 4-dimensional vector. Now, matrix C, which is the concatenation of both linear transformations, of course, matrix C must be necessarily a 4 times 3 matrix, 4 rows and 3 columns. Why? Because it starts with 3-dimensional vectors and it ends with 4-dimensional vectors. Okay? So the size of the matrix when you do the multiplication makes perfect sense if you follow the logic of the number of dimensions in each step. Okay? Now, of course, this means that you cannot multiply matrices if the dimensions don't match. So for example, if someone asks you to multiply these two matrices, the answer is cannot be done. Dimensions don't match. Let me show you this in a nice example. If you go to a computer program such as Wolfram Mathematica, where you can do multiplications of matrices, and you try to do this multiplication, what you get is an error message. Tensors this and this have incompatible shapes, so you cannot do it, okay? The nice thing about this is that it's very easy to deduce this or to quickly notice this problem when you are using the trick that I just showed you. So if I move this, so if you try to use the trick, you immediately see that you cannot do this multiplication, because when you try to write the first element here, you say, okay, I need to do the dot product between this row and this column. How do you do the dot product of those two things if they don't have the same number of elements? So you cannot do it. Error. You cannot do it. You cannot do it. Dimensions don't match. Okay. Does it make sense geometrically? Well, of course it makes sense. So in this case, we are having a 3x3 matrix, which is getting 3-dimensional vectors and converting them to 3-dimensional vectors. And then we are trying to apply after that, so this is matrix A. And then after that, we are trying to apply matrix B, which is a 3x2 matrix, okay? Now, a 3x2 matrix is a matrix that starts with 2-dimensional vectors and ends up with 3-dimensional vectors. So matrix B works on 2-dimensional vectors. It cannot work on 3-dimensional vectors, which is the output of A. So that's why you cannot multiply those two matrices, because the dimensions don't match. Okay? Okay, see you in the next video.